Hello and welcome to this video on Booth's algorithm. In this video, we will be discussing how this algorithm works and how it can be used to multiply signed binary numbers efficiently. These are my group members, myself roll number 7 Sahil Jadhav, roll number 8 Sanika Jadhav, roll number 9 Sarvesh Jadhav, roll number 10 Shivendra Jadhav, roll number 11 Shreyas Jadhav, roll number 12 Shubham Jadhav. This is the basic overview of this video. First, we will be discussing the introduction of Booth's algorithm, then we will see its objectives, examples, and then advantages and disadvantages. Let's start with introduction. Booth's algorithm is a multiplication algorithm that is used to multiply two signed binary numbers in two's complement notation. It was developed by Andrew Donald Booth in 1950 and is widely used in computer science today. Booth's algorithm is particularly useful for multiplying large numbers as it requires fewer arithmetic operations than other multiplication algorithms. It also has the ability to handle overflow and underflow situations. The algorithm works by repeatedly adding one of two values to a product register based on the values of adjacent bits in the two input numbers. The two values are -1 and +1 times the second input number, the multiplier, and the choice of which value to add depends on the value of the rightmost bit in the product register. Booth's algorithm is commonly used in digital signal processing, cryptography, and other areas of computer science where large numbers need to be multiplied efficiently. It is important for computer scientists to understand Booth's algorithm and how it can be used as it is a fundamental algorithm in the field of computer science. Note that Booth's algorithm can be used to multiply both positive and negative numbers and can handle overflow and underflow situations. It is also more efficient than other multiplication algorithms for large numbers since it requires fewer arithmetic operations. Next slide will be explained by Sarvesh Yadav.
Multiplication algorithm is a technique for multiplying two numbers using binary arithmetic. The primary objective of the Booth's multiplication algorithm is to reduce the number of additions and subtractions required to compute the product of two numbers. Specifically, the algorithm aims to minimize the number of partial products that need to be added together to obtain the final result. The algorithm achieves this objective by exploiting the redundancy in the binary representation of the multiplier. By using a modified representation of the multiplier, the algorithm can perform additions and subtractions more effectively, reducing the overall number of operations required. In addition to reducing the number of arithmetic operations, the Booth multiplication algorithm can also be used to optimize the hardware implementation of a multiplier. By minimizing the number of partial products and reducing the number of required adders and multipliers, the algorithm can help to reduce the complexity and cost of hardware implementations. Overall, the Booth's multiplication algorithm aims to improve the efficiency and performance of a binary multiplication, making it a useful tool in many applications, including digital signal processing, cryptography, and computer graphics.
Let's learn about Booth algorithm for multiplication. So before going directly to the example, we have to learn about what is the actually methodology and algorithm for a Booth algorithm. So this is the flow chart for a Booth algorithm. We have to start from the basic, and in accumulator we have to store initially 0, and a flip flop named as a q minus we have to store 0. In the m and q, they are both are register, and we have to store multiplicand and multiply respectively. In count, we have a number of bits. When q is not and q minus 1, which are q naught is equal to lsp of the multiplier, and q minus 1 is the flip flop. When they are 0 0 or 1 1, we have to do arithmetic right shift and decrement count by the 1. When they are 1 and 0, in the content of the accumulator, we have to store content of accumulator plus second complement of the multiplicand, and plus right shift and decrement of count value of count by 1. When they are 0 and 1, we have to do addition of multiplicand and the content of accumulator and store this value in the accumulator, and again do arithmetic right shift and the decrement count by 1. When count is equal to 0, we have to end this process. But when they are not equal to 0, we have to again do same task. We have to do right shift and check whether q naught and q minus 1 are 1 0 0 1 or 0 0 or 1 1. So let's take an example on the Booth's algorithm. We have in example minus 11 into 4. In the multiplicand as a m, we have to store 11 1 0 1 1. We have to take second complement of multiplicand, which is 1 0 1 0 1, and then multiply we have q as a 0 1 0 0. In the logic we can say when the q naught and q minus 1 are 0 1, we have to do addition of content in accumulator plus multiplicand, then right shift. When they are 1 and 0, we have to do addition of second complement of multiplicand plus content in accumulator, then right shift. When 0 0 and 1 1 come, and in place of q naught and q minus 1, we have to do right shift and decrement count by 1. In the A, initially the 0 0, q is a 1 0 1 0 0, and q minus 1 initially 0, and number of bits are 4. In the q naught is equal to LSB of q is a 0, and the q naught q minus 1 is 0, then we have to do right shift in the uh, in upcoming operation. Then n and decrement count by 1. The n is equal to 3. After the right shift, we get this value. In the n is equal to 3, we have q LSB as a 0 and q minus 1 as a 0. Again, we have to do a right shift and a decrement count by 2. 1. Sorry. In the accumulator again, after we get at the accumulator as a 0 0 0, and the q LSB of q is a 1 and q minus 1 initially is a 0, then it is a 1 0. By algorithm we have to do addition of a content in accumulator and the second complement of m, and again a right shift. Then we get and a decrement count by 1. Then we get n, which is number of bit as equal to 1, and the value of accumulator as a 1 0 1 0, and LSB of the q as a 0, and q minus 1 is equal to 1. Then we get q naught and q minus 1 as a 0 and 1, and we have to do now a content addition of content of accumulator plus multiplicand, and then right shift and decrement n by 1. Then count is equal to 0, and we have to end this process, and we get an accumulator answer of this question as a 0 0 1 0 1 1 0 0, which is the binary value of the decimal value 44. Thank you.
Let's take the example of 6 into 5. The multiplicand m is 6 and the multiplier q is 5. 6 in binary is 0 1 1 0 and 5 is 0 1 0 1. For the minus m means minus 6, we will get the we will take the ones complement of the 6 and add 1, so we will get 1 0 1 0. The basic logic of the multiplication is based on the least significant bit of the multiplier, and the previous bit means q minus 1. So if we have 0 and 1, then we will perform a plus m operation, and then further we will perform the right shift operation. And for the 1 0, we will perform a minus m operation, and then we will perform the right shift operation. If both of them is same as 0 0 or 1 1, we will just perform the right shift operation. The number of bits is equal to number of passes, so we have 4 bits, therefore the number of passes will be 4. In the fourth pass, we initialize the accumulator a with 0 and also the minus 1 with 0. Now the least significant bit of the q is 1, and for q minus 1 is 0. For the 1 0, we will perform a minus m operation, and we will get 1 0 1 0, which will get stored in accumulator, and we will perform the right shift operation. For the third pass, we will have least significant bit as 0, and q minus 1 we have 1. For 0 1, we will perform a plus m operation, and we will get 0 0 1 1, which will get stored in accumulator, and we will perform the right shift operation. Further, after the third pass, we have 1 and 0 as the least significant bits, so we will perform a minus m operation, and we will get 1 0 1 1, which will get stored in accumulator, and further we perform the right shift operation. So now in the last pass, the least significant bit of the multiplier is 0 and the q minus 1 as 1. For the 0 1, we will perform a plus m operation, and we will get 0 0 1 1, which will get stored in accumulator, and we will perform the right shift operation. So the final answer is the combination of A means accumulator and Q multiplier. In the binary we have 0001111110 is the final answer. When we convert this binary in the decimal format, we will get 30 as the final answer. So 6 into 5 is equal to 30.
So we will be discussing the advantages of Booth's algorithm, a method for performing multiplication of two signed binary numbers in 2's complement notation. Firstly, Booth's algorithm is efficient and fast as it reduces the number of additions and shifts required to perform the multiplication compared to other algorithms. This makes it particularly useful for large numbers. Secondly, Booth's algorithm naturally presents the result in selective way due to its use of partial product generation. This allows for the selective addition and subtraction of multiplies of the multiplier, which can be useful in certain applications where only specific bit of the product are needed. Thirdly, Booth's algorithm simplifies the multiplication process by reducing the number of partial products generated. This can be especially useful when performing multiplication by hand. Fourthly, Booth's algorithm produces a product with fewer bits than the usual multiplication algorithm. This is particularly useful in applications where storage space is limited. Fifthly, Booth's algorithm improves the accuracy of multiplication, especially when working with large numbers due to its use of partial product generation. In addition, Booth's algorithm is relatively easy to implement in hardware, making it a popular choice of digital circuits and processors. Furthermore, it can reduce power consumption in certain hardware implementations due to the reduced number of operations required to perform the multiplication.
Now moving on to the disadvantages, limited parallelism. Booth's algorithm has limited parallelism because the algorithm steps must be executed sequentially. So each step relies on the result of the previous step, which restricts the ability to perform multiple operations simultaneously. Second one is limited hardware efficiency. So Booth's algorithm requires additional hardware components such as registers and control logic to implement the algorithm steps. This can increase the hardware complexity and potentially affect efficiency, especially when compared to other multiplication algorithms. Next is reduced precision. Here the Booth's algorithm uses a signed digit representation for numbers, which reduces the precision compared to other multiplication techniques. This reduction in precision may lead to a loss of accuracy in the final result. Fourth one is limited speed. Although Booth's algorithm can provide faster multiplication for certain types of numbers, such as numbers with a large number of zeros in their binary representation, it may not always be the fastest algorithm. Other multiplication algorithms, such as Karatsuba multiplication or Fourier transform based methods, can outperform Booth's algorithm in certain scenarios. Fifth is limited scalability. Booth's algorithm is primarily suitable for fixed point multiplication of specific word sizes. It may not be easily scalable to handle large number or different data formats. So as a result, its applicability and efficiency may be limited when working with more complex arithmetic operations or sometimes larger data sizes. So overall, while Booth's algorithm has advantages in specific cases, such as signed multiplication or numbers with specific patterns, it also has certain limitations that make it less ideal in other scenarios where parallelism, hardware efficiency, precision, speed, and scalability are crucial factors.